And let's actually think about this by starting up here. Suppose that I asked you to solve, how about this? X cubed equals 3. What would you do to solve that? What is the solution to that?
Cube root 3.
The cube root of 3. And if you like, the cube root is just a name for the solution to that equation. What if I asked you to solve x squared equal to 5? We have a function that undoes squaring, except it doesn't really undo squaring. It's off by a plus or minus sign. What if you wanted to solve something that looked like e to the x equal to 25? What's the solution to that? Right? And that's why we introduced the natural law of the logarithmic functions. We wanted to undo exponentials. Let's do the exact same thing with trig functions. Well, I guess that's also down here. If you want to solve exponentials, we needed inverses. In order to solve something like 3 to the x equals 5, we said x is the log base 3 of 5. To solve sine of x is equal to 1/8, right, there is some angle which gives you a sine of 1/8. We'll just need to make up a name for it. That's what we'll do today. And first, let's start by seeing that there's something silly in what I'm trying to do. One of those is sine and one of those is cosine. Which one is sine, which one's cosine? That one's sine? So it goes through 0, 0. Do those two functions pass the horizontal line test? So are they one-to-one? Do they have inverse functions? No. So that automatically says that something's weird. Because I want inverse functions to those, but they don't have inverse functions, so I'm trying to study something that doesn't exist. But we've encountered this before, and we know exactly how to fix it. There's the graph of y equals x squared. Is that function one-to-one? No. So it also doesn't have an inverse function. But we know how to undo squaring. What operation undoes the squaring function? Square root. Up to dealing with this, like there might be a plus or minus sign issue. And that's exactly what we'll do. And here's the philosophy behind it. So maybe I'll put it over here, but square root undoes squaring. There's the same function. There's the graph of y equals x squared, but I've restricted the domain to be the interval from 0 to infinity. Does that graph pass the horizontal line test?
Yes.
Yes. So is that function one-to-one? Does that function have an inverse function? Yeah, and you in fact know what that inverse function is. What is the inverse to that function? It's the square root function. Is it one-to-one? Yes. Does it have an inverse function? Yes. What is its inverse function? It's the square root of x. So restricting the domain of something that you know isn't one-to-one to make it one-to-one is really useful. Is it like out of focus? I see a lot of people squinting. Ah, that's because I haven't done this. Better? I'll hit this also. I think that often helps. Oh, and is it recording? It is recording. Let me move the screen down a little bit. Cool. So I'll do the same thing. I'm going to restrict the domain of sine and the domain of cosine to make them one-to-one. And let's just see how to do it by looking up here. So starting at 0, 0 is a good number to have in the domain. How far to the right can you go before this function stops being one-to-one? You can make it till about this point. So if I go just up to pi over 2 and stop, then if you just look at what I've highlighted in green, maybe you can't tell it's green on the projected screen. That's 1 to 1. How far back from 0 can I go while still having to be 1 to 1?
Negative pi over 2.
Negative pi over 2. So if I only sketch that much of the graph, I should have something that's 1 to 1. And there is exactly that zoomed in. Let's do the same thing for cosine. So let's start at x equals 0. How far to the right from x equals 0 can I go while still having this function be 1 to 1? Pi, because that's where that next taunting point is. So if I can make it to here, just that green highlighted bit is 1 to 1. So there's sine of x from negative pi over 2 to pi over 2. There's cosine of x from x equals 0 to x equals pi. And let's forget everything else about sine and cosine. Let's just remember those chunks of the graphs for some of today. This function, the function given by this graph, what is its domain? Negative pi over 2 to pi over 2, because I've restricted the domain. I said I'm only going to permit those x values. Domain is negative pi over 2 to pi over 2. What is its range?
Negative 1.
Negative 1 to 1. And this is 1 to 1. There's cosine. I've restricted its domain to be the interval from 0 to pi. And I still see its range hits all y values from negative 1 up to 1. So, are these 1 to 1? They are. Do they have inverses? Yeah, because they're 1 to 1. Yeah, bingo. These are the functions that I'll study. Sine inverse, also called arcsine, is by definition the inverse to that function. It's the inverse to sine of x. Once you restrict the domain of sine of x to negative pi over 2 to pi over 2. Inverse cosine, also called arc cosine, is the inverse to cosine when you restrict the domain of cosine to the interval from 0 to pi. Everyone pretty happy about that? Nice. Maybe I'll point out sine inverse is not 1 over sine of x. We have an int 1 over sine of x. What is 1 over sine of x? Cosecant. So remember, that negative 1 means I want the inverse function.
You're off the screen.
I'm off the screen. I don't know why this is too high. I think it's washing out too quickly when I slide. Is it still readable? Oh. Okay. Because now when I do this, yeah, it doesn't wash out. Nice. So let's read off some stuff. So up there's the domain of sine after I've restricted the domain. The domain is negative pi over 2 to pi over 2. The range is negative 1 to 1. I want to study the inverse to that function. What is the domain of the inverse to that function? Should be the same as the range of the original. So the range of the original appears to be negative 1 to 1. So the domain of inverse sine of x is the same as the range of sine, which is negative 1 to 1. What is the range of inverse sine of x? It'll be the domain of sine of x after we restrict the domain. So what is that range? So this is the same as the restricted domain. Negative pi over 2 to pi over 2. Same thing for cosine. What is the range of, start with domain. What is the domain of inverse cosine? same as the range of cosine, which is negative 1 to 1. What's the range of inverse cosine? Zero to pi. So let's just think about what that means. That means if you want to compute, say, the inverse sine of something, the thing you trying to compute the inverse sine of had better be between negative 1 and positive 1. Otherwise, it's not in the domain. What you're asking doesn't make sense. The output is then always going to be a number between negative pi over 2 and pi over 2. So if you're trying to solve a problem, and you're looking for an angle, if you use inverse sine somewhere in your computation, the angle you produce will be an angle that's between negative pi over 2 and pi over 2. So you should think about whether that's actually the angle you want when you're proceeding. Otherwise, you're going to need to do some more tripping. Everyone with me so far? Everyone happy? Any questions right now? Nice. So I think the next thing that I want to do is graph these functions. I'm going to circle that because, as I noticed after I printed them out, there was an error there. So there's the graph of sine and of cosine. What should that blue point actually be? The one that I circled? Pi over 2 comma 0? That's where the x-intercept of cosine is? That point is pi over 2 comma 0. Oh, you know, so I did correct it after I printed it, but I think I didn't correct everything. I don't think I actually replaced that negative 1 with a 0. So if you're looking at it online right now, which I don't think anyone is, that would be a strange thing to do if you just had the notes pulled up on the screen while I was talking around the paper. It's still on. How do you get the graph of an inverse function given the graph of a function? Flip the x's one. So the x coordinates will become y coordinates, the y coordinates will become x coordinates. Let's just trace out where some of these points will go. So if this point, negative pi over 2 comma negative 1 is on the graph of sine, then what point will be on the graph of inverse sine? Negative 1, negative pi over 2. There it is. And you'll see right here that if you like, the slope of this curve is like really close to 0, so it's almost horizontal. So the slope of the inverse will be really close to vertical. So it'll be almost vertical. Right here I see the point 0, comma 0 on the graph of sine. So what point should be on the graph of inverse sine? 0, 0. Fair enough. And it'll come up and hit the point at 1, comma pi over 2. Do you think we can do the same thing and generate the graph of inverse cosine? Yeah, of course. Just take all those coordinates, flip them. So I guess this point at pi over 2 comma 0, where will that point go, pi over 2 comma 0, when I flip the x and y coordinates? 0 comma pi over 2. So there's the graph of inverse sine and inverse cosine. Any questions right now about what we've done? And the motivating thing that you should remember is these are the things that you'll need if you want to study solutions to trig equations. So just keep that in mind for motivation. We'll do a bit of that motivation just at the bottom of this page. So we've defined inverse sine and inverse cosine once already as the inverses to sine and cosine after you restrict the domain. So let's try to incorporate that a little bit. So if you like, this is like translating between exponential and logarithmic notation. If someone says that the log base b of x is equal to y, how can you rewrite that in terms of exponentials? e to the y is equal to x. Similarly, if someone says that, let's do inverse. if someone says the inverse sine of x is equal to y, can you rewrite that in terms of sine instead of inverse sine? Yeah. Almost, anyway. There's only one defect here. What's the range of inverse sine? Nope, you're talking the domain of inverse sine. Negative pi over 2 to pi over 2. So this output y is equal to an inverse sine. So that y is somewhere between negative pi over 2 and pi over 2. Cool. So with that in mind, let's just write that down. If I give you an x value between -1 and 1, which you need to have if you're going to talk about inverse sine, that's the domain of inverse sine. If you say that the inverse sine of x is equal to theta, so here I've called it theta, means that the sine of theta is equal to this input x, and theta is between negative pi over 2 and pi over 2. Everybody feel pretty okay right now? So you can translate from trig equations to inverse trig equations and back again, as long as you keep track of this domain constraint. Similarly, if you fix an x between -1 and 1 and you say cosine of x is equal to theta, well, that should mean that cosine of theta is equal to x, and theta should be like between some numbers. What's the range of inverse cosine? 0 to pi. So what should that theta be between? And you'll notice that I was being needlessly vague. Let's add a bit of detail right there. Should I include those endpoints or exclude them? Include. Because the endpoints are in the domain for this particular function. There are solid dots. Nice. So that means that we can, by hand, directly compute some inverse trig functions. Let's try to compute the inverse cosine of 1/2. And let's do it by translating that a little bit. So theta equals cosine inverse of 1/2 means cosine of theta is equal to 1/2, and theta is in 0, pi. So look at your unit circle. Do you see an angle which produces a cosine of 1/2? Yeah, say it louder.
60 degrees.
But you also said pi over 3, which is the answer I really wanted anyway. Ooh, so you can do all of this inverse trigonometry in degree mode instead of a radian mode, if you want to. And if you do that, then all of these numbers that I've been saying, all of the pi's should actually be, I guess, like 180 degrees. But I will only walk in radians. If you want to walk in degrees, then translate to radians, walk in radians, and then translate back if you want to. Let's do it again. Compute for me the inverse sine of -1/2. So let's start with this. Find some theta with sine theta equal to -1/2. -1/2. Let's draw that unit circle.
Pi over 6, pi over 4, pi over 3.
None of these will be it, right? Those will all produce positive y values.
2 pi over 3, 3 pi over 4, 5 pi over 6.
Again, positive y values.
7 pi over 6, 5 pi over 3, 5 pi over 4 pi over 3.
Aha, these have negative y values. Let's list those points. What point goes here?
2 over 2.
Does this give me an angle which has the right value of cosine?
Yes.
Yes, you're shaking your head because this isn't the angle I want. But so I'll write down a thing which is incorrect. Well, theta equal to 7 pi over 6 seems to walk. But why is that not the right answer to this question? It's not in the, well, it's not in the range. Right, it needs to be between negative pi over 2 and pi over 2. Is that number between negative pi over 2 and pi over 2? In fact, let's think about it this way. If you look at the unit circle, what quadrants does negative pi over 2 to pi over 2 trace out? 1 and 4, right? There's negative pi over 2, there's pi over 2. I want something in quadrant 1 or quadrant 4. How can I take this point and get it into quadrant 1 or quadrant 4? And I guess, so one could then rewrite this angle as, I think it's written on your unit circle, if you have the one that I gave out, as 11 pi over 6. So is the answer to this question 11 pi over 6?
Yes.
Anyone want to say no? Why do you want to say no? Yeah, the number itself needs to be between negative pi over 2 and pi over 2. So this is, if you like, it's like the right direction. It's the point on the unit circle that we want. But we're off by a 2 pi. So how should we rewrite that 11 pi over 6 to get something between negative pi over 2 and pi over 2? We should write it.
Negative pi.
Yeah. Walks, but this is in the wrong range. So a second guess would be 11 pi over 6, but it is still in the wrong range. So we need to settle on theta equal to negative pi over 6. And we'll think about how to systematically compute these things. But in some sense, what we just did is exactly what you need to do. Is the angle you produce in the right quadrant? If not, do a reflection to get it into an acceptable quadrant. Is the angle you want off by some 2 pi's? If so, add or subtract some 2 pi's till you get into the right range. Nice. Everyone feel okay? How many people have unit circle on them today? How many people do not? Okay. Well, looking at your unit circle, or the unit circle of someone around you, because not too many people brought their hands up or don't have the unit circle. Let's fill in some inputs in, if you like, a lookup table for inverse trig functions. So let's just try to do some computations. Let's try to compute inverse cosine of negative 1. So that means I want an angle which produces a cosine of negative 1. Looking at your unit circle, what angle produces a cosine of negative 1? Pi walks. And let's see, we want a number that's between 0 and pi. Is pi between 0 and pi? Yeah, because, like I said, we want to include those endpoints. So what's the inverse cosine of negative 1? Pi? And we've already done a few others. Inverse cosine of 1/2 appears to be pi over 3. Inverse sine of negative 1/2 appears to be negative pi over 6. And now I'll give you guys two options. I can have you guys wake up and do some of the computations, or I can talk through some more of the computations until we notice some paths. Want me to keep talking? Okay. Okay, seeing some hands go up, I will suggest this. If you don't want to listen to me, then maybe I'll say, you guys do inverse sine, you guys do inverse cosine, and I'll just start with some values and try to figure out what should go in each place. So maybe I'll start by, I don't know, I'll just grab one at random. I'll walk out negative pi over 2 pi over 2 for both cosine and sine. So I'll start by filling in my unit circle.
Also known as negative pi over 2, 7 pi over 4, or negative pi over 4, depending on how you want to think of it, negative pi over 6, or 11 pi over 6, depending on how you want to think of it.
Let's fill this in. So if we want to produce inverse cosine of negative root 2 over 2, I need an angle which produces a cosine of negative root 2 over 2. And I think there are 2 points that have that. There's this one,
And this one.
fair enough. What's the range of inverse cosine? Zero to pi. Between 3 pi over 4 and 5 pi over 4, does one of those live between 0 and pi? Yeah, which one? 3 pi over 4. Cool. So what's the inverse cosine of negative the square root of 2 over 2? People feel like they followed that process? Okay, so now what I think I want to do is, some of you haven't been listening, so I think I'll go left to right, and you guys will tell me what you got. What is the inverse sine of negative 1? Negative pi over 2. So if you want to get to negative 1, you should rotate down to negative pi over 2 to get there. What is the inverse cosine of negative the square root of 3 over 2? 5 pi over 6. And you can see that, right? So inverse cosine of negative 1 was pi. Then we rotate back here to 5 pi over 6, where we see negative, where we see, oh, that negative sign is wrong with, where we see this point, negative root 3 over 2 comma 1/2. Inverse sine of negative root 3 over 2. Cool, and I think I'll say one more, we'll do one more out loud, and then I'll just write in left to right. Inverse sine of negative root 2 over 2. And maybe you notice something? Sine seems to be reading angles in, inverse sine is reading the angles in this order. Inverse cosine is just reading the angles on the unit circle in that order. So we can just fill this in. After 3 pi over 4 is 2 pi over 3. pi over 2 for 0. For root 2 over 2, pi over 4, pi over 6, 0. Inverse sine of 0 is 0. And in fact, we see that on the graph. Inverse sine of 0 is 0. Oh, nope, that graph. Inverse sine of 1/2 is pi over 6. Inverse sine of, what am I doing? Pi over 4, pi over 3, pi over 2. People feel pretty good about that table? And in fact, where those numbers came from? To the point where I don't think on a note card you even need that lookup table, do you? The unit circle is the lookup table. Just remember what quadrant you're supposed to look in. So in order to see what these things are for, let's actually do something with inverse trig functions. So there's a triangle. Let's try to determine this angle theta. So by looking at that triangle, what trig function can you tell me? Cosine. What is the cosine of that angle? Let's think if that angle lives in the right range. Is that angle theta somewhere between 0 and pi? Yeah, in fact, it should be somewhere between 0 and a right angle, right? So it should be somewhere between 0 and pi over 2. So that angle is in the range of inverse cosine. So by using inverse trigonometry, what does that angle have to be? Well, let's see. Saying inverse cosine of an angle is equal to a number, and theta is between 0 and pi, means that we can rewrite that equation in inverse trig form. That theta is inverse cosine of x. So this theta is cosine inverse of 4 over 5. How do people feel about that? Does that seem okay? Well, if you wanted to know the approximate value of this angle, 4 over 5 isn't a number that I see in the lookup table. So if you want to actually do a computation, I'll come now. That's not what I want. Let's compute it. Let's compute arc cosine of 4 over 5. Somewhere around 6.4 radians. Well, I guess we've been walking in radians the whole time, so I don't need to specify. People pretty okay with that? That seems reasonable? Let's take a short segue and let's notice a few other things. What's the other side length on that triangle? 50. So what other trig functions at theta can you determine? Yeah, I guess. How about sine? What is the sine of that angle theta? 3/5. Is the angle theta somewhere between negative pi over 2 and pi over 2? Yeah, in fact, it's between 0 and pi over 2, so even better. So on the one hand, we know that this angle theta is the inverse cosine of 4/5, but what is it in terms of inverse sine? Yeah, this theta is the inverse sine of 3/5. Which maybe we can even do a quick sanity check. Is that the same number again? Cool. Do you think there's probably some sort of function called arctangent that I'm avoiding talking about right now? So let's see. Those of you who are reliant on their calculators for doing some computations, are you aware of how to compute inverse trig functions using your forward computational device? Does anyone know? There's probably a button on your front screen that says something like arc cosine or cosine inverse. At your leisure, take a look at your machine. See what it says. Cool. So, I think maybe I'll jump down a little bit. Let's think about what happens when you compose a trig function with an inverse trig function. And I don't know, let's just see what intuition people have. What should the cosine of the inverse cosine of a number be, do you think? It should probably be that number. Like, trig functions should undo inverse trig functions. What if I go in the other order? The inverse sine of the sine of a number. What do you think that should be? Presumably. But you know that something can possibly go wrong. Because what is... So if I take the square root of some number x and then I square it, what do I get back? Oh, yeah. Is that always x? That's not the issue here, right? Both of those are functions, so it is defined. Except for what happens if you plug in x equals like -7. Not defined. So there's a domain issue here. What if you take x and you square it and then you take the square root of it? Is that always equal to x? Let's see. So let's start with 5. Take x equals 5. What's 5 squared? What's the square root of 25? So that walked out. Let's try -7. What's -7 squared? 49. What's the square root of 49? Did I get the same input back again? No. So, like, some weird stuff can happen. In fact, the square root of x squared isn't always x. It's, in fact, always the absolute value of x. So, when you do this stuff, some funkiness can happen. And let's try to explore exactly what that funkiness can be. So let's compute some stuff from the inside out. Let's try to compute the cosine of the inverse cosine of 1 over 2. And let's not try to be clever about it. Let's just try to use lookup tables. There's a lookup table for inverse cosine on the previous page. What's the inverse cosine of 1 over 2 by looking at that lookup table? Yeah, let's say it loud. Pi over 3. What's the cosine of pi over 3? Yeah, sorry. Apparently I'm really bad at that today. Or maybe I'm just really bad at that all the time. Yeah, so it walked out in this case. Good. Inverse, the sine of the inverse sine of -1. What's the inverse sine of -1? What's the sine of -pi over 2? So it checks out. I think I'll add one other to reveal what can go on. What's the cosine of the inverse cosine of 67? Let's try to think that through. What's the domain of inverse cosine? -1 to 1. Is 67 between -1 and 1? So this is cosine of something undefined. So there's a domain issue. So it is in fact true that the cosine of the inverse cosine of x is always equal to x. The sine of the inverse sine of x is always equal to x. Provided that x is actually something where you can compute the inverse trig functions in question. Any questions right now? Let's try to switch the order of the two. Let's try to compute the inverse cosine of the cosine of some things. And let's, I don't know, maybe we'll do an example of one where it actually walks out. Let's try to compute first. How about the inverse cosine of the cosine of pi over 3? Let's try to compute that. What's the cosine of pi over 3? It's not the 1/2 over 3 over 2, right? Which is it? So this is the same as cosine inverse of 1/2. What's the inverse cosine of 1/2? Pi over 3. So it walks out in this case. So as long as you have a number that's in the right range, yeah, inverse cosine is going to undo cosine. But not all of the numbers you can plug into this formula will be in the right range to have it walk out. Let's try to compute inverse cosine of the cosine of pi over 3. What's the cosine of pi over, what? Nope. What I wrote, not what I said. Let's try to compute the inverse cosine of the cosine of 3 pi. What's the cosine of 3 pi? What's the inverse cosine of -1? So that's not 3 pi again. So in fact, the answer to this is cosine of inverse cosine of x always equal to x. Well, the answer is yes-ish, but there's a domain issue. Is the inverse sine of the sine of x always equal to x? No. It is sometimes. Let's do one last one. The inverse sine of the sine of 5 pi over 3. Let's try to compute that. What's the sine of 5 pi over 3? -√3/2 by looking at your unit circle. By looking at that lookup table that you have, what's the inverse sine of negative the square root of 3/2? Did you say 2 or 3? 3. Okay. So, is the inverse sine of the sine of a number always that same number you start with? In fact, let's actually sketch a graph of these things and see what we get. So let's go online, let's graph the inverse sine of the sine, let's just call that x. Let's forget that these are supposed to be angles at all. And let's even specify a domain. The domain is -2 pi to 2 pi. And those of you who wish to, who have graphing calculators, should graph along. I'll go ahead and pull it up on this. By the magic of television, I've already entered in the query that I want. There's the inverse sine of the sine of x. There it is. It's like this weird sawtooth function. So there's the graph of the inverse sine of the sine of x. Oh, you know what? I'm actually going to flip these two. I'm going to do something that's maybe annoying. I'll make that y equals inverse cosine of x. I'll make that y equals inverse sine of the sine of x. So we see straight line of slope 1, straight line of slope -1, straight line of slope 1, straight line of slope -1, going out in both directions. Well, I've screwed up the domain, so I won't indicate that. And let's just track down where those first couple turning points are by looking at the graph. So it looks like there's a turning point up there. Where approximately would you say that that turning point is? pi over 2, I think. So I see this turning point here at pi over 2, comma pi over 2. I see this turning point down here at, oh, yeah. I see this turning point down here at negative pi over 2, comma negative pi over 2. So it looks like during this stretch, it does look like y equals x. But otherwise, it looks like it has a weird piecewise linear definition. It's built out of a bunch of straight lines. Any questions right now? Let's also just get the graph of cosine inverse of the cosine of x. Do you think we'll get a similar looking function? Yeah, I think it'll look kind of sort of the same. In fact, let's put it on the same place. Let's plot those two functions. Son of a diddly. Oh, there's a parentheses issue. Should be fine. Wow. This is the trouble with me trying to do anything live with the computer. There it is. So there's the graph of cosine of inverse cosine of x. What about does it look like this point right here is 2 pi? And then you think it's just going to repeat that same sawtoothness on the way out? Well, yeah. So I just sketched it. It went through the point 0, 0, pi, pi, and then 2 pi comma 0. And then it repeated that pattern. Oh, okay. So I did intend this to be more than a one-day lecture, and it looks like I've hit my time quota for today. So what are we going to? What's left to do today? I want to think about, well, it looks like these functions, sine inverse of sine and cosine inverse of cosine, are like complicated. What I'm going to do tomorrow is we'll talk about, well, if I give you the sine inverse of the sine of 25 pi over 7, how do you compute it? Cool. So I'm going to stop because I'm done. And in terms of exams, like I said before, they're mostly all graded and marked up. I hope to have them in today. If you're impatient, then I have an office hour at 2, 1. And you can come see me then. Thank you. If you happen to be really impatient and want to know how you did on the exam and can't make the office hour, shoot me an email. I can give you at least preliminary numbers.